not change because we have
When you want, you can start. Yeah.
I can start now?
Yes, you can start now.
Okay. Hello, everyone, and welcome to the first session of our workshop. This session will talk about emerging architectures and technologies, and we have three very interesting papers. We'll start with the first one, Network on Metachip Architectures. The presenter is Ismo Hanninen, who received his MSc degree in Information Technology in 2004 and the Doctor of Technology degree in 2009 from Tampere University of Technology in Finland. He's currently visiting the Center for Nanoscience and Technology at the University of Notre Dame, the USA, as a guest professor for the current academic year. He's on a sabbatical from his position as a postdoctoral research fellow in computer engineering at Tampere University in Finland. His research interests include nanotechnology circuits, computer arithmetic, and embedded systems design. Ismo, thank you.
So, good morning. This speak will be about network architectures and implementations on a Metachip physical system. And first, I would like to thank my co-authors and the researchers of Center for Nanoscience and Technology at the University of Notre Dame, USA, Wayne Buckhanan and Michael Niemier and Gary Bernstein. I would also like to thank Jason Kulik of the Indiana Integrated Circuits for contributing to this talk on Metachip architectures. To start with, I would like to give you an introduction into our concept of Metachip chips and the quilt packaging, which is a registered trademark of the Indiana Integrated Circuits, a spin-off from the University of Notre Dame, aiming to improve and advance the development of the prototype systems of these Metachips. I would like to continue then with describing the signal performance on these physical implementations we have measured, followed by determining some limitations and opportunities the Metachips offer. Several important use cases covered will be the memory access on a quilted Metachip, since memory access is one of the bottlenecks typically in a multiprocessor system on chip. And then I will show you a couple of proposals for a general architecture for a multiprocessor quilted system. But first, let's start to look at what are the Metachips. We are talking about a two-dimensional circuit integration method that is competing with the 3D stacking of chips and through silicon vias. But the principle and implementation, fabrication of the quilts is more straightforward compared to the three-dimensional technologies. The basic QP quilt packaging concept is to directly connect the chips at their edges together with nodules. So we can use this complementary to on-chip stacking and other packaging technologies. And we can form a hybrid system with stacking, bumping, or through silicon vias, even optical interconnects and wire bonds. So the dies are connected together from their edges, separate dies manufactured. Some applications where quilt packaging could be used are heterogeneous integration of systems where the chips are made from different material systems, like 3 to 5 PD array, typically for gallium arsenide, lasers, radio frequency components, this type of things. Heterogeneous integration of substrates and process technologies is a significant advantage of quilt packaging. So we can really fabricate these chips separately with their corresponding technologies and then integrate them together as a quilt. The nodules which are used to connect the quilts are created in what would normally be the saw streets on a silicon wafer between the dies. They can be formed in many ways, but the best approach for inserting the quilt packaging into a chip process would be to complete first the front end of chip fabrication and put these nodules in at the same point where you would have via middle approach connections. So in this picture, the red areas represent the finished front end of the chip fabrication, and then we'll get the nodules in between on the saw streets. The QP process is very similar to via middle, with etching, plating, and polishing all occurring between the front and back end of the line. First, we start with etching the places for the nodules, plating them, drawing interconnects on a metal layer from them into the chip, and then etching the saw streets and thinning and dicing the wafer. So die are typically singulated using a dry etch process rather than the saw in a process combined with back grind, like analogous to dies before grind. And then when we have the quilted chips put together in a multiprocessor chip or a heterogeneous chip, we can handle the quilt as if it were a single monolithic chip. It can be wire bonded, bumped, stacked, and placed into a standard or custom package, depending on the applications we are aiming at. So the quilted approach is conforming to all the standard IC fabrication tools, the robotic tools for assembly and automatic handling of the chips and packages. So in that manner, the incorporating of the quilting is pretty straightforward into the typical IC process. So the tools are already ready from all major suppliers. Some major advantages of the Metachips and quilt packaging are first the heterogeneous integration, where you can get all types of components with different technologies living together inside a single package. Then for processor systems, one of the most important benefits would be thermal control due to having all the chips on a single planar cooling element. So it's a major pro combined, for example, to 3D stacking of chips. So far, it seems to be that three-dimensional cooling has a lot of challenges, but if we can place the chips on a plane, we can use a standard heat sink to get the heat away from there. And that's one of the pros. I'll have to mention the high signal bandwidth and signal integrity at this point, but I'll come back to them in a moment. One major good point is compared to a system where you combine separate chips, separate packages together, is that with quilt packaging we can get rid of the signal I/O drivers and pads and all the capacitance and power consumption related to them. So with quilt packaging, we have the quilted interconnections that are nearly on chip in their quality and also in their power consumption to drive them. Typically, fabrication costs are really reduced by eliminating the package costs and also board complexities if we can integrate this into a system on a Metachip, which is packaged in a single pack. Typically, also with increasing the integration density, we would be able to get rid of some of electrical noise related to driving signals outside, also decrease need for passives. So in the following, I want to show you a couple of pictures of the physical implementations of the prototypes that have been made at the Notre Dame and have been currently characterized and measured there. The interconnection nodules can be made in many geometries. And here are a couple of slides showing physical implementations. On the left side, there is a 25 micron wide signal nodules right next to 200 micron wide ground nodules. So you can have on a single chip edge different sizes and different types of interconnections. On the right, there is a stitching pattern showing a digital bus 25 micron wide nodules for interconnections. And then on the bottom, there's a 10 micron wide and 20 micron thick interconnection nodules also, which would aim for a digital bus preferably. It seems to be very feasible that the nodules can be made as small as 2.5 microns in their width, and this translates to quite high density of the interconnects between there. Currently, 5 micron is the smallest that has been fabricated, but we feel pretty confident that 2.5 micron width is reasonable. But also, in addition to the single straight interconnection nodules between the chips, we could use keyed nodules. And if we form these kind of keyed nodules, we can use them to get chip-to-chip alignment that has sub-micron accuracy. So you can just mechanically put the quilted chips together and they will interlock very accurately together. This is excellent property, and you could imagine a chip edge where you would have these sort of interlocking alignment nodules and digital buses and ground connections, power connections, all different sizes, where the designers would not be limited to the approach that one size fits all, which you would have to use for wire bonds or bump sizes if you go outside the package or combine the chips that way. The nodules are amazingly strong. Here's a picture of the standard 10 micrometer nodules, which have about 18 micrometer anchor inside the silicon. And when we put two of these chips together with these straight nodules, the mechanical robustness is such that we can lift one of the chips with vacuum tweezers up, and still the second chip follows with it. So you could almost bend it and the chips could still stay together. And this is with the basic copper nodules that have nothing extra notches on them. They have been just thin soldered together. If you use interlocking nodules, you could actually end up having even more strength there. Even with straight nodules, the interconnection mechanical strength is more than the copper itself. At Notre Dame, we have conducted some pull tests with the nodules, and it turned out that the 18 micrometer anchor is so tightly combined or attached to the silicon that the copper nodule itself broke before it was pulled out of the silicon. So if you combine that with interlocking nodules, perhaps more complex geometries like this, you can imagine that you can integrate the chips pretty robustly together so that they are almost like one matter. Another thing, although quilt packaging is competing with three-dimensional stacking, nothing prevents to use them together. Here's a three-dimensional quilted concept where you would make a motherboard, mother chip, and attach daughter chips with the nodules into that, and then glue it all together with an epoxy film. Then you would have a three-dimensional chip fabricated this way. Here's one example how you could do it. Of course, nothing prevents you from stacking the two-dimensional metachips on top of each other. So this approach is really can be combined with the emerging 3D technologies too. When we consider computing systems, one of the most important things is the signal performance, what we can expect. If we go outside a chip or package, there will be some parasitics and power consumption related to driving the signal out. But with quilt packaging, we can avoid quite a lot of that. So we have conducted some measurements on characterizing the signal quality that can be handled between two quilted chips. And it turns out that the signal performance is excellent. First, let's look at the radio frequency performance. There's a typical two 100 micrometer nodules connected together, and they are copper and they are soldered together with tin, 1 micrometer solder. These electrical measurements have been taken at Notre Dame, and we have included some of the results just for you to quickly see the performance. Here's the radio frequency insertion loss measured in the test setup. And it seems to be that the loss that can be attributed to the interconnection nodules between chips is about 0.1 decibels until you reach about 110 gigahertz. If you look at the blue curve, you can see what the test pads alone affect for this chip. And adding the nodules to that really changed the picture very little. So the loss is very low. For intrinsic quilt packaged radio frequency performance, here's a graph that where we have removed the effect of pads and launcher. So this graph is the RF response of only the nodules between the chips. And it seems to be that it's less than 0.1 decibels to 100 gigahertz is the loss. And the loss is very flat versus the frequency characteristics here. So you could imagine that you could probably use these nodules to transmit a very high quality radio signal just into the another part of the chip. For example, if you have an antenna on one quilt, you could pass the signal through the nodules with very small amount of loss. Here's a picture of the return loss. It's consistent with the increased transmission line length, the resonance point. But we are also interested to look how it compares to other technologies. So here's the quilt packaged de-embedded insertion loss compared with other types of connecting chips, wire bond, small bit array, and also flip chip. So for compared to the normalized loss, it seems to be that quilt packaging and the nodules really reach the world record or set the world record for low loss chip-to-chip interconnect. So the other types of connections have significantly more loss, RF loss, than comes with the nodules. But we are also very interested in the digital buses and how they can be implemented with the nodules. And we have conducted some measurements on the time domain performance. The nodules seem to increase the delay about 2.7 picoseconds, which corresponds to a clock frequency of more than 300 gigahertz. So I would say that for a bus, that's very insignificant delay. And also, if we look at the eye diagrams with pseudo-random patterns, here are a couple of measurements conducted at the Notre Dame of the eye diagrams of the digital signaling with a 32-bit pseudo-random generator as a source. While these two eye diagrams look very similar, they are not the same. The top image is actually the output of the pattern generator put directly into the bit error tester, while the second image is the eye diagram of the quilted or signal that has been through the nodule interconnections. So based on these measurements, the nodules are really electrically transparent for the digital buses. So the only thing what you see is the delay that seems to correspond quite directly to the distance, how far you are going, how far you are driving the signal. And that's the same for all technologies. With this type of interconnection characteristics, I will present you next some calculations on what can be achieved with the Metachip architectures. For example, what are the numbers of interconnects we could incorporate? If we would make homogeneous digital buses with the nodules, we could typically accommodate about 50 to 200 nodules per millimeter of chip edge. And this directly translates to having thousands of interconnections between chip edge that is about a centimeter wide. But the homogeneous bus structure is not any necessity, because we can put also the ground wires and also optical interconnections and radio frequency wires through the chip interconnect. But just if you would like to make a digital bus, you would have thousands of the interconnections available there. The next question is, how much does it cost if we look at the silicon area? Here are a couple of graphs, how much area on the wafer you would have to reserve for making the nodules and the source streets between the chips. Especially on the right side figure, it can be seen that the ratio of the nodule area compared to the total chip area is something less than 1% typically. So you could say that the nodules consume about the same amount of area on a chip than would be consumed for the source streets on a wafer without the nodules. So you can practically always fit them in the source streets that would be there anyway if you would make that size chips on a wafer. The anchor depth is one of the parameters that sets the nodule area consumption, but in all the cases we quickly end up under 1%, especially with centimeter class chips. If we compare this silicon area loss to the yield, what could be expected from a deep submicron technology, it's pretty insignificant. On the left side graph, there's plotted the yield-induced loss of silicon area compared to the chip size for several uniform defect rates. They actually form a quite nice curves from one point to another. But if you have a defect rate of about 1 per 10,000 or 1 per 1,000 defects per square millimeters, you would quickly end up having unacceptable amount of working chips. You would aim more than about 1 centimeter times 1 centimeter size with the chips. So this is a simple calculation on a Poisson yield model of integrated circuits. If you compare the loss that becomes quite high with increasing chip size, if you compare that to the loss inherent to making the source treats and nodules, you can see that the nodule overhead is very small, where you easily, with the high defect rates, end up having a lot of unusable chips on the wafer. So the idea with building a Metachip would be that you would use a lot smaller chips, and for that you would get higher yield of silicon, and you could still combine the same system out of those quilts. So just a quick look on how to implement memory access on a quilt. We ran just a small amount of simulations on a quilted system where we had a processor model and a memory model that had been simulated, and actual Spec 2000 benchmark memory intensive code was run on it. It turned out that just compared to external memories, the benefit from moving the memory into a quilt can be around 10 to 20%, which corresponds quite closely to a physical system on chip implementation. So in that sense, a Metachip functions as performs as well as a monolithic system on chip, but it's much more easier to fabricate, or you get much better yield for it. And then we also searched the literature for the size of memory cells typically, and it turned out that the embedded variants of DRAM and SRAM are quite large compared to the typical DRAM cell which you would have in an external memory module. So if you are building a system on chip with embedded DRAM or SRAM, you would usually consume about 10 to 20 times the amount of area which you would be compared to the DRAM as a separate chip. So we propose that with quilt packaging you could actually include in the system standard DRAM that has been fabricated with the best possible memory technology, and then quilted into the processor chip, and you would have the memory density that's comparable to off-chip memories, but you would still have the wide boost fast access, which is related to a system on chip implementation. And based on these ideas, we propose a couple of multiprocessor systems. These are very preliminary systems. We have run some simulations on system models, but these have not been fabricated. First idea would be to build a multiprocessor signal processing system that's using the embedded processors and then separate memory chips quilted together for pipeline type of signal processing applications. The main benefit here is that you can have the components manufactured with the best possible technology for that specific type of component. The memory, the processor, also the I/O areas of the chip. You would not be limited to having you would not have to be able to do everything on the same chip, which is very difficult for example, the memories. Another of our proposals is to use a network of quilts, tiles, to build a more extensive multiprocessor system. And here is only one picture of the proposed design. But the rationale of partitioning the system into this type of array is that now you would be able to create network-on-chip quilts that would have been manufactured only aiming at the network functionality. So you would be able to design routing inside an NoQ quilt, or for example the deadlock detection inside an NOC quilt, and it would be something that you could optimize very highly independent of the processors and memories and other stuff there. Also here is visible a heterogeneous antenna component and also analog radio frequency processor in this picture. So this is just to get an idea what you could expect out of a quilted system. The result is that the system designer has much more freedom to explore the design space when he is not limited so much by the technology limitations, sticking to a single technology, and also the designer is not limited for the problem of low yield of large integrated circuits. But you could really split up the design into quilts, so you would make one large quilt out of, for example, 64 of small chips that are very easy to manufacture. You get very high yields. So with this I want to move to conclusion. So quilt packaging typically provides excellent signal integrity and bandwidth for both analog and digital systems, and provides savings in the amount of silicon you have available for the system. And applications include all the signal processing systems and multiprocessor systems, and the complexity is limited only by the imagination of the designer. Mapping the system on chip and network to a practical physical chip determines the economy of fabricating the system. And the Metachips generally improve this economy, and the only cost is the small cost of the source treats, and then an increased cost in the fabrication complexity where you insert the nodule step. But that's a reasonably simple step compared to the other steps that are involved in IC fabrication. One of the good features is that you can utilize wide buses for memory, so you can have systems on chip with faster memory and larger because of the density you gain by using external memory chips. And also the network on chip with the complexity as high as you can imagine it. Now, actually I want to, at this point, conclude with leaving the, throwing the ball back to you and asking where would you like to use this type of technology? Because we have only scratched the surface of the systems on Metachips. Thank you.
So do we have any questions? Yes?
The question is that when you actually integrate it in time, sort of everything, is it possible to make replacement of the chips within the Metachip? whether if after some testing or debugging you can sort of determine some.
So the question was, if we have a Metachip, can you replace a broken
That's right.
quilt in the middle of the chip? I think in principle that is possible, although if you solder the nodules together with, for example, tin, then removing the solder might be a difficulty. But generally, if you use the notched interlocking nodules, you can connect them with very good electrical properties, even completely without solder, so that they are just mechanically interlocking. So that way, you can remove them, moving to the right direction. So in principle, it should be possible. So even after combining the quilt, you could still repair it.
And what is your expectation of this Metachip, the entire size of it? Just how big
Well,
you can?
Well,
in terms of
currently the largest chips that have been fabricated at Notre Dame are 4 centimeters times 2 centimeters. But that's just a limit of prototyping. Nothing prevents you from making the Metachip as large as the chip handling equipment usually is capable of handling. So safely you can say that you can have at least 4 centimeters times 4 centimeter chips, perhaps even larger. But at least for 4 times 4 centimeters, the equipment is ready for all handling.
Any more questions? Okay, let's thank our speaker once again.